Okay, I'm going to talk about a class of problems involving the position vector r. So I think there's a good argument to be made, but this is the most important vector field in existence. And another candidate might be the gradient operator, which you can do cross products and dot products with, but I think that might be cheating. So I still think I'm right when I'm saying this. So, and let me just give you a couple of reasons why. If you look at a point charge from electromagnetism, certainly it'll obey Coulomb's law, where the force will be given by an inverse square law. This is radial, and it depends just on our favorite vector field divided by its length cubed. And actually, the same exact force appears remarkably in gravity. This is now the gravitational force for a point mass. So again, our vector field divided by its length cubed, it showed up in very important physical settings. So these are things you'll see in upper division, and frankly, these are things that influence your daily life. And so the idea of these class of problems will be to consider calculus with these functions, kinds of functions. And these will show up in all of your upper division courses involving where you need calculus, because this is such a fundamental vector field. So let's do it. Let's do a couple. So an example problem will be something like this. Calculate the divergence of our position vector field. Calculate the divergence of our position vector field scaled by some factor. Remember, our forces are scaled by r cubed, so that's a good motivation. And then finally, compute the Laplacian of r cubed. Remember, a Laplacian is just the dot product with the gradient. And this is super important. Laplacian is because as it turns out, the Laplacian of this quantity is 0. Or rather, I think I should the divergence of this. The divergence of this thing is 0, and the Laplacian of 1 over r is 0. So this is clearly not true for r cubed, but it's good to get some familiarity with the Laplacian. So let's do it. So the divergence of r is d dx, and remember r is just x, y, z. So this is d dx of x plus d dy of y plus d dz of z. So this is just 3. It turns out if you do this in any dimension, you'll get n for exactly the same reason. But let's use this for our second calculation. For this, what I'm going to do is I'm going to use the product rule. Because remember, we are always lazy. We never do things the honest way. The honest way would be to expand and use that square root. I would not do this. It's honest, but we always like to be lazy. So the product rule says it's the first times the derivative of the second plus the second times the derivative of the first. So we already know what the first term is. That's just 3. For the second term, you may have seen this calculation before, but let's just look at the x component. And everything else will be similar by symmetry. So this should surely just be x divided by that square root. So in other words, if you look at all the components, it will just be the position vector divided by that length. So we have 3r plus r dot r divided by r. It's a lot of r's, but really it just reduces to 1. So we just have one more calculation to do, and it is the Laplacian of r cubed. And as usual, I highly recommend being lazy. By the definition of the Laplacian, we know it's just the divergence of the gradient. So it's the gradient of r cubed. So by the chain rule, it's the divergence of 3r squared. That's the derivative. Now we take the chain, gradient r. And we actually did the gradient of r back here. So these calculations are kind of stacking on themselves. So we know it's just something with 0 dimensions. R divided by r. So it's the divergence of 3r squared, r over r. Obviously, we get some cancellation here, which is kind of nice. So this is 3rr. But look, we actually did that. We did that right here, right? So this is just 4r. So it's 3 times 4r, we get 12r. So hopefully that was a nice prelude to some of the calculations you will see in upper division courses. Thanks for watching.